So in the last video, we introduced this idea of angular momentum conservation with a sort of before and after framing in the case where there are no external torques applied. And what I want to do in this video is actually think about a case where we do have external torques applied and look at this sort of example of a bouncing ball, which will require us both to think about linear impulse and to think about angular impulse. Okay? So let's think about this sort of ideal case where I have this ball. It's coming along, it interacts with the floor, so it has some initial velocity in the y direction and in the x direction, right? And let's say it's not spinning initially, and then after the bounce, it's flying up into the air. It's got some new velocity that has some component in the x direction, some component in the y direction, and since it wasn't spinning before it hit the ground, we would imagine that this point will be moving forward relative to the ground, so there'll be a frictional force acting on it backwards, so we'd also imagine that it's going to be spinning with some angular velocity, omega f, right? And notice that that will be actually negative. It'll be going into the page because of the fact that it's spinning clockwise. Okay, so that's the sort of hypothetical example, right? Ball comes along, bounces, right? This is the sort of thing that we talked about in one of the in-class exercises. So how do we think about this from a sort of momentum conservation perspective? Well, the first thing that we might say is, well, we know how the final velocity in the y direction will compare to the final velocity in the x direction. Let's assume that there's this sort of particular coefficient of restitution. And what the coefficient of restitution tells us is that the velocity in the y direction afterwards is some constant times the speed in the y direction before, right? Now this is simply a model that people commonly use for bouncing objects. It's not anything other than a phenomenological model, but let's assume that that's actually the case, right? If that is the case, what that tells us is that the change in momentum in the y direction, right? The y component of the change in momentum is the final velocity in the y direction, so plus alpha times vy initial, minus what the momentum was in the y direction, so it's in the j hat direction, minus negative vyi j hat, right? Because initially the ball was traveling down at some initial velocity in the y direction. Afterwards it's traveling up at some fraction of that velocity in the y direction. So in other words, the change in y momentum is 1 plus alpha times the initial speed in the y direction. Notice that at this point we could say something about what was going on during the interaction, right? This implies that there was some normal force that gave us an impulse, right? So delta py will be the integral of the normal force over the time of the interaction, right? And that impulse tells us what that change is, right? So 1 plus alpha times vy initial, okay? So we know how much normal impulse there was. Well, if we think about that, we could think about what that normal force might look like, right? The normal force here versus time, right? Well, the ball will be coming through the air. While the ball is in the air, there's no normal force. Then the ball hits, the normal force goes up, it comes back down, right? So it looks something like that. This is going to be pretty big. It'll be substantially greater than mg, right? Because the ball actually is accelerating upwards much faster than the gravitational acceleration. Note that that also tells us something about what we might imagine the frictional impulse looks like, right? There'll also be some frictional force, and that frictional force will be in the negative I hat direction, but it will be proportional to what the normal force is, right? If we assume that it's always slipping, if it's always slipping, this value will be mu k times the normal force, which in turn tells us that since we've got an impulse in the x direction as well, that we're going to have a change in what the x momentum is, right? And that x momentum actually will be, the change in the x momentum will be proportional to what the change in the y momentum is. In other words, the change in the x direction momentum will be 1 plus alpha times what the coefficient of friction is times Vy initial. Right. This will be a negative change in the I hat direction. This will be a positive change in the J hat direction. Because of course the X momentum will be reduced due to the fact the ball is coming in like this, sliding against the ground that way, giving me a force in that direction, so the X momentum will be slowed down by a certain amount. Right? So in other words, I would say that Vx final would be equal to Vx initial minus, oh, I forgot my masses here. Sorry, I should have had a mass here and a mass here, but will be Vx initial minus mu k times 1 plus alpha times Vy initial. Right? And if we actually check the units here, now that I put my masses back in, this is mass times a dimensionless constant times velocity, dimensionless constant times mass, dimensionless constant velocity, velocity, velocity. Right? Okay. So now I know what my final momentum in the x direction is if I know what my final momentum in the y direction is, right? Or if I know what my coefficient of restitution is. Now, so far we've just been talking about conservation of linear momentum, but let's also think about conservation of angular momentum here. My initial angular momentum of the ball about the center mass of the ball is 0. When I say about the center mass of the ball, what I'm actually doing is I'm considering a coordinate system where I'm thinking about the origin being the center of mass of the ball, and I'm thinking about some frictional force that's being applied here at the edge of the ball. Right? So my initial center momentum, angular momentum is 0. Right? The ball is not rotating. My final angular momentum about the center of mass is going to be given by minus omega f times the moment of inertia in the k hat direction. Right? It's going to be going into the page, and that final angular momentum will be equal to my initial angular momentum plus whatever the angular impulse is. Well, I know what the linear impulse in the x direction is, right? It's that big, which is equal to the integral of this frictional force. And notice that the amount of torque that I'm actually getting is simply that frictional force times the radius of the ball. So that implies that the angular impulse is simply going to be the amount of linear impulse in the x direction, so delta px times the radius of the ball. And you'll notice that this is actually a negative quantity, right? Px is decreasing, the delta px is negative, so my torque here indeed is going to give me a negative value, and so in fact my final angular momentum of the ball, my final angular velocity of the ball will be equal to the change in what the x velocity is times the radius divided by the moment of inertia. So here what we've done is you basically use the idea of momentum conservation and angular momentum conservation to figure out the final state of the system. We've got a before case where the ball has some particular set of momenta and angular momenta. We have some interaction that involves a force in the x direction, a force in the y direction, and a torque. Right? And the torque, notice, is simply a constant. So it's minus r times the frictional force magnitude. And since we have an impulse in the y direction, that gives us a change in the momentum in the y direction. Since we have an impulse in the x direction, that gives us a change in momentum in the x direction. And since we have an impulse, angular impulse, that gives us a change in what the angular momentum is, and finally in what the angular velocity is. And I should have had a k hat there.